So the plan for today is we will continue the lecture on the what we were hierarchical modeling. I know that we are halfway through the Jags code that we were talking about last time. So I want to finish talking about that and also discuss the possibility of doing a more complicated hierarchical model where the sigmas are also being set up a two-stage prior. And then I will talk a little bit about the I would want to talk a little bit also about the lab 4, which is going to be practicing for you all in teams again, how to use Jags to run hierarchical models. And I will spend some time talking about the models themselves a little bit. They are still the hierarchical models that we're dealing with right now, but we're going to ask you to practice using different priors, okay, to fit the hierarchical model. So that will give you the chance to look at how to write certain distribution for the prior, for example, in Jags, because that could be quite different in terms of syntax and how things can be done compared to the basic R that we have been doing. So I want to give you the chance to practice that as well. So that will be the focus for lab 4. And once we talk about the lecture, we'll spend some time on the lab itself and then give you the time to work on whether it's lab 3 that you're working on or homework 4 that you're working on or lab 4 that you want to start on already. Okay, so that's the plan for today. So where we were off last time is this Jags script. Okay, so we spent some time, asked you in the breakout room to discuss how each chunk of the code is doing. And then we also spend time together in a whole class, talk about specific steps and all that. So basically, the main chunk of doing Jags is this model string, okay, where you're gonna have a chunk for the data model, where is the likelihood. You're also gonna have a chunk for priors. And in our particular case right now, we also have the chunk for the hyperpriors, because if you remember for our two-stage prior from MuJ, we have the priors themselves and also the hyperpriors for the hyperparameters. So in general, I think you will see at least 2 chunks, okay, when you're writing a Jags script. You will always have the modeling step, which is the likelihood part. And you're always gonna have a chunk about the priors, and sometimes you might have an additional chunk for the hyperpriors. So I think if you put them separate and then chunk by chunk, hopefully it will match well to, so let me go back to the previous slide where we actually had the data model. So you can see that the chunk 2 about the priors is about the MuJs here and also about the sigma, okay? And then the hyperprior section that we have in the Jags code is in the box here about the hyperpriors that we use for the hyperparameters. And then, of course, you have the data model going on, which is before that we talked about, and then that goes into the data model over here in terms of likelihood. Okay, so if you sort through all of the different aspects and I think components of your model, then the Jags script should be very descriptive of what you're doing. Okay, so I think it's always a good practice to compare back and forth to make sure that you're indeed doing the thing that you think you're doing. And then that will help a lot in case later on you figure your model and find some issues about it. And then it's always a good indication of how to go back to debug what happened not correctly previously. Okay. So those are the notes that we, I think, ended on Wednesday. So there are certain things in particular for our case, because we have the MuJ, each of them follows a normal prior. So we actually need a vector of MuJ, okay, instead of just one scalar. And the length of that MuJ is going to be capital J. That's the number of groups, which is 4 in our data set. And also, if you remember, coming back to the code that we had earlier, because each of the data, so let me write that chunk one more time. Mathematically, we wrote Yij, right, follows a normal with MuJ and sigma. So sigma is shared across the different schedules. The MuJ is going to be group specific. Okay, so we write one single loop over here. Okay, and we use dnorm because that's the density for the normal that we're dealing over here. And specifically, we're using the MuJ as a vector. And we need to determine which J this observation I belongs to. So if you're able to pass the schedule of each observation as a vector as well, you'll be able to extract which MuJ that you should be working on. Okay, so that's the trick, I think, or the newest part I think, in this chunk of code that compared to before, we are having some more, I guess, fancier way of coding things. And don't forget, which is another note that we have over here, whenever you're working with D norm, it takes mean and the precision. That's why we have that inverse sigma 2, and also inverse tau 2. Okay, so that's the reason why we had those terms earlier. And lastly, if you work with inverse gamma square or inverse gamma 2 over here, you can also return the sigma itself if that's what you want to track later, and similarly for tau. Okay, so those are the new, I think, updates that we're doing in this set of code compared to what we did Jags for, I think, the simple normal model before, whereas here we're doing the hierarchical. So like I said, when you work on lab 4, I think you will get to practice learning about each of the pieces a little bit more in detail. But I want to highlight early on that those are the new things that you should pay attention to as we are learning this chunk. Okay. So the model string is the main part, like I said. You have that ready, and then you need to also pass the data, pass all of the parameter values that you want to use to get it started. So that's why we always have another chunk, like what we're doing over here. So for example, the ratings, okay, we're storing everything into what we call Y. Remember, we also want a schedule vector. Okay, so we're also getting the schedule vector over here coming from the data set. We have that capital N to represent the total number of observations because we need that in the loop. Okay, so that should be another quantity that you want to pass. And lastly, J is the number of groups. So one thing you could do is you can calculate or return the number of unique schedules, and then take the length of that thing. You will get the number of different schedules, which we know is 4 in the data. Okay, but that will be a quick way in R to get it. Another thing we haven't talked about before, which I want to introduce now here, is how to get reproducible results when you're working with Jags. Okay. So in basic R, we all know that if you do set seed before a random process, you set whatever value that you want. And then if you keep running that, no matter how many times you get, you will get the same results. Okay, so in basic R, that's what you do. Okay, Jags works differently. Like if you want, you can give it a try, set a seed before running a Jags part, but you will never get reproducible results because it does not take seed in that way. The particular way that Jags is doing over here, I think it's so it's a little bit complicated, but I set this as a sample code that you can always use if you want to set a particular way to set seed. So you can use that. So you will see how we're going to use it. But this whole chunk itself is trying to help us to get reproducible results. Okay. So Jags has a specific way of doing that. And this is one thing you can do. Lastly, we have seen this before, but specifically, we're going to pass the data, everything together into the Jags code to run it. So remember, in our model string, we have Y, we have schedule. We also have the capital N, that's the number of observations, the number of groups. And all of this are those hyperparameters that we need just to get the model to work. So you specify them in the data list, and then you can pass everything into Jags. So you'll be able to use Jags to estimate your MCMC. So like I said, we have seen this once before in the previous lecture on Gibbs sampler, where we're introducing how to use Jags to write Gibbs sampler. So the basic flow is still the same. So for example, you're always going to have a model string, okay? And you're always going to have a, preparing the data. We're introducing this new thing about how to get reproducible results, but you're also going to pass all of the other values that you want for each of the quantities that you have over there. So this is going to be similar to what we have seen before, but I think we didn't practice doing Jags in the previous lecture, but in this lecture, this will be the focus, especially in lab 4, when you get to do the details of trying different drivers and all that. So the next chunk that we usually do, you remember, is run Jags. Okay, so you have your model string. That's what you prepare beforehand. As long as it's correct, it should be fine. You can specify the number of chains, right? You want to determine how many chains you want to run. In our illustration, we're just going to do one round chain. The data, earlier, the whole list is whatever we're going to pass to the data part. And monitor, if you remember, it is the list of all of the parameters you want to track in your MCMC. So for us, we have the mu, we have tau. We also have all of the mu j's that we want to track, as well as the last sigma. Okay, so whatever goes into here should be what you want to track later as well. So if you remember, we have all of the mu j's as a vector, okay? And each of the mu j follows a normal prior with mu as the mean and tau as the standard deviation. So we track those two as well, okay? And lastly, we also have the overall sigma for each of the data model that we're getting. The rest should be straightforward. We have the adapt, the burn-in period, the sample period, and also the thinning. Okay. So the thinning, I think, okay, so first of all, the burn-in, if you remember, is the first however many draws that you want to toss out before you start to summarize your posterior. Sample, as we know, is the final number of iterations that you want to have. Thin is something that you might have to revisit after you check the diagnostics, because if you have very highly correlated draws, you might have to go back to this step and then increase the value of thin. So you'll be able to have more independent draws and all that. The only new thing here, I think, is inish, okay? So in this over here is the reproducible set seed step that Jags specifically takes. So this will be the new thing that you want to add if you ever want to get reproducible results. So like I said, basically, you always have the model string that represents what the model you're working with, okay? You have the place that you're going to prepare the data and all of the details, and then you have the last part over here to actually use the round Jags function from the round Jags R package to actually get the posterior draws that you want. And then this should look similar to what we have done before, but of course, the specific parameters that you're trying to monitor, the specific number of burn-in, sample, and thinning, as well as the initial values. We call it initial values, but you can think about it really as a reproducible setup. Okay. All right. So with that, let's finally take a look at some of the outcomes and results, I guess. And then we can evaluate whether we actually need to, for example, increase the thin a little bit after we check the MCMC diagnostics. So let's look at this together. So as we know, you can always do a quick summary of the entire posterior. We know that each row represents a particular parameter that you're tracking. Okay, so if you remember, we tracked mu, we tracked tau, we tracked mu j, and there are 4 different mu j, so they actually show them to you one by one to you, okay, because we have different mu j's, one mu j for a particular group, and then we also have a final sigma. Okay, so that's why you have this, how many? Yeah, 7 rows in total. Okay. And for each of them, as we know, they give you the middle 90% credible interval, give you the median of that parameter, the mean, the standard deviation, et cetera, et cetera. For us, it's important, I think, to also always check the effective sample size. If you remember this quantity, this is trying to make sure that we have enough independent draws in the posterior to summarize. Okay, so we have 5,000 iterations in total for the sample. And you can see that almost all of them are pretty independent from each other. One thing interesting I would say is this one. And I remember when we were talking about MCMC diagnostics in the previous lecture, some of you were asking, oh, would I ever get any effective sample size that is actually larger than the number of samples that we got? So this is an example that sometimes you do, because the autocorrelation sometimes can be negative, and then the way that the effective sample size is being calculated might not reflect that per se, so that will increase the number of effective sample size actually to be greater than the 5,000. But nevertheless, this is the important column to check to make sure that you indeed have relatively independent posterior draws before you actually start to summarize what the outcomes are. Okay, make sense? Make sense? All right, let's look at some plots. And I will probably also just give you the chance to talk to your neighbors a little bit. So this is the 4 plots, if you remember. We usually, when you do plot of the posterior and then select a particular parameter, it will give you the 4 different plots. Okay, so this is what we call place plot, right? And this is a autocorrelation plot, right? And this is a regular density plot. And that's an empirical CDF. We don't read it as much. So I think the most important is this 2, as we talked about before. So given this 2, talk to your neighbors, and I will put people on the breakout room, remote in the breakout room as well, whether you think it's reasonable to think that the MCMC diagnostics are passed, so we can move on to the next step. And we'll do that for another parameter later as well. So let's spend 1 to 2 minutes-ish on this, and then we're gonna resume. All right, so any comments about this mu J1? This is the mu J for the first group, which is, I think, the first schedule. That's what, Monday, Tuesday, I think, the broadcasting schedule. Any thoughts about, or any comments about if there are any issues with the MCMC mixing, or not so much, so we can maybe move on? Any issues? Not really? Okay, I see a lot of raising hands. Yes, so I guess specifically if we look at the autocorrelation plot, ACF down here, okay, that shows, well, you start with 0 with yourself, but then it dies down pretty quickly. Okay, so that indicates that, well, the thing equals to 1 is probably pretty fine. And we also saw that on the effective sample size earlier, that column, so it's not surprising that here the ACF doesn't show any problem, I should say. And the trace plot seems also overall exploring this parameter space, okay? And you can also see actually from this left bottom, that's the density plot itself, which is the histogram, I think, and then you can roughly see where the mu1 or mu J1 lies. Okay, somewhere around 0, I think, if we look at the histogram over here. Overall, these are the two, the diagonal here, those are the two that we should focus on checking the MCMC diagnostics. And overall, it seems fine for mu J1. I think I have another one for tau, so that's the that is the hyperparameter, if you remember. Okay, that is the standard deviation that we give in the normal prior for the mean. Okay, so if you remember how we did it, if mu J follows normal, that's our first stage of the prior that we have. Okay, so that's the tau that we're tracking over here. Overall, it seems fine. I would say as well, seems to be dying down relatively quickly. If you're a little bit concerned, like to say with the black ones, you might want to set your thing to be 2 and rerun it if that's what your concern is about. But overall, it seems fine. But the trace plot is kind of interesting, I would say, because overall it is, stabilizing in the lower part, right? But occasionally you do jump out a little bit to the top. So that might be another indication of you might want to set the thin a little bit. I mean, together with the ACF down here, you might want to set the thin just to see if you want to increase it to be 2 or 5 or something, and then that can get rid of that a little bit more. Okay, so this probably is the first example that we have seen that, well, MCMC diagnostics is suggesting some kind of going back and then redo your setup on. Okay. I think in the slides I only include tau and mu J1, but you should do that for all of the parameters, okay, making sure that they're all passed before you can move on to say that, well, our MCMC estimation is done, so we can do further analysis as we wish. Okay. So that's the MCMC diagnostics. Another thing I want to come back maybe quickly here is that, remember, we have our model. We have each observation follows a normal with a specific mu J and a shared sigma. And then we have our prior, right? For the mu J to be mu and tau. And then we have sigma to be 1 over sigma square is the gamma of certain things. I forgot the number of the parameters and all that. But nevertheless, I want to just ask you to rethink what the results actually is telling us. Because mu J, if you remember, is the average, right? Is the average rating of each group. That's what mu J represents in the first place. We give them the same prior as we started. Do the posterior from the printout that we're seeing over here, showing us that, well, how the mu J's are different from each other. And does that make sense to you given the results that we're seeing? Okay, so let me repeat the question. So here we have the posterior. Okay, the posterior is after we run the hierarchical model MCMC estimation, we start to have posterior distributions, right? Here are the summaries. The summary is about the mu J. The question is, do the mu J look quite similar to each other or maybe not so much in the posterior? And what do they tell you about the analysis of the data itself? So our data, if you remember, is the ratings of dramas that is from, they're all from the same broadcasting company, KBS, I think, but they are viewed or they're broadcasted on 4 different schedules. Okay, so our question now, I guess, is, do you think that the schedule or the ratings do change a lot across different schedules, or maybe not so much. So that will be an actual question that we can discuss a little bit before we move on to talk about other aspects of the hierarchical model. Okay. So take a moment. I think this will be one type of summary that you can look at. Earlier, we showed you the summary or like the histogram of one of the mu-j's. So if you return all of the mu-j's, you can also analyze over there. But I think for the interest of time and also just for the space, you can use this summary to take a look. And I should also ask if you see any problematic issues jumping out of the summary that you think that the model might not be the best, or we might need to do some adjustment accordingly. Okay, so it's a multi-part question, and I will pause here and I will give the remote students the breakout room as well. All right, so maybe first part first, do you think the mu-j's, which represent the average of the ratings, okay, given, or I should say by the schedule, do they look similar in the posterior or maybe not so much, given the printout of the summary over here? Any thoughts? Similar, not similar? Somewhat similar? What column we should be looking at, or what are the columns that we can look at? Yes, Adam?
Like they all have different means and medians, like that looks pretty significant, but then also the confidence intervals like contain 0.
Yeah.
So that you can, you know,
Yeah,
kind of
good
figure it
point.
out.
Yeah, so first of all, we can look at the median and the mean. Well, depends. So that's why I think it's always also useful to do the plotting that we did earlier as well, because, well, you can decide whether you want to use the mean or median, depending on how symmetric the distribution is. But nevertheless, I think they overall tell a similar story. Okay, if we look at the median across the 4 different schedules, mu-j's, and the mean as well, very clearly different, with the last one being the highest. Okay, and then the second is the second one is the second, and then the first, and then the third. And if you actually just compare them in the magnitude, the last one is almost like 5 times as higher, okay, as the third and all that. So this probably tells us, based on this Bayesian analysis using the hierarchical model, we can say that mu-j4, or I guess the mean rating of the schedule 4 is the highest, okay, as high as about 20% in the posterior, in the mean and median-ish. Whereas the third one, which is the Friday one, if you remember, right, we have a small sample size over there, as well as I think overall very low in the data as well as the average. So overall, I think is telling us something not very different from what the data is saying. Okay? So you can see that this Bayesian analysis in particular, I think, is probably heavily driven by the data itself, even though we have a prior and all that. But nevertheless, I think it helps us to understand the mu-j3, for example, a little bit more, because we know that in the data set, there are only 3 data points over there. Now we could borrow information by doing this hierarchical model when we're saying that all of the mu-j's are coming from the same distribution. Okay. And it also talked about the interval. So a small correction over here. Here should be a credible interval instead of confidence intervals, because we're dealing with the Bayesian context. But nevertheless, all of them contain 0. Okay, if we look at the lower bound to the upper bound. So, well, if you're doing a hypothesis test, as we know, then you will check, well, okay, there are certain things that mu-j, for example, might not be significantly different from 0, as we are looking at the credible interval in this case. But I do want to ask, given what Aidan talked about, do we see anything problematic about the analysis that we have done over here? I mean, 0 is a starting point, because clearly all of them do contain 0, in a sense that all of the lower bounds of all of the mu-j's, and also for the mu, by the way, all of them are negative. Do that make sense in our context, or maybe not so much? Sarah?
Well, I mean, since it's ratings, you can't have, I mean, any ratings that are at least less than 0. So it doesn't really make sense to use a model which would produce outcomes that would be negative.
Yeah, great point. And I remember on Wednesday, even though I didn't know exactly what the rating is about, but one of us, I think a remote student from Swarthmore, Koji, was pointing out that it's a percentage. Okay, so the ratings themselves, they are percentages. And I think percentage of viewers and all that. So in theory, we should never get anything less than 0, or yeah, shouldn't be anything negative. So this is actually an important lesson learned, because if we look at how we actually set up the model, which I wrote at the top left, right over here, hopefully is readable enough, okay? We set the data model to be following a normal, still overall, I think still makes sense, right? If we're normal and all that, it's a numerical data. And then we also set the MuJ to be another normal. So I think even the data and parameter type, giving normal is not a bad idea. But we might want to do some kind of manipulation about the normal model itself to make sure that we don't get anything, or we do not allow any of the MuJ to be negative in the first place. Okay? As we know, MuJ is there at the means. They're in the means of the ratings. If the ratings cannot be negative, the means should not be negative either. Okay, so that will be the focus in lab 4, which we will talk about it towards the end of today's lecture as well, is that there are other remedies that you can do to make sure that you are giving sensible prior that will make sure that the results are reasonable. Okay, so for example, even though normal prior is not a bad idea to start with, because it's a continuous quantity, the MuJ, but normal itself does not guarantee that the quantity is going to be positive, right? But you could do some other, for example, now we have Jags, you do not need to follow the normal itself anymore. Okay, you could use other priors that will be making MuJ, like you force MuJ to be never a, or should say, should always be a positive quantity. If you specify that in the prior, then the MCMC down by Jags will also enforce that as well. So in the posterior, it will never be negative as well. Okay, so in the lab, you will see different ways to do it. I think one of the methods that I introduced is called truncated normal. Okay, so instead of getting normal on the entire real line, so for example, in normal density, even though let's just say if 0 is here, we center at, I don't know, 2 or something, you might still have some quantity, right? Less than 0, even if you are giving a normal like this. So the truncated normal distribution is literally truncating the normal only to the positive side. Okay? So that could be a reasonable, right? Prior for MuJ, if you want to give it a try. So that's one of the priors that we're going to explore in lab 4. And in lab 4, I propose another possible distribution altogether for the MuJ is called the log normal distribution. Okay, so on the log scale, you follow a normal distribution. So on the original scale, you're going to be top. Okay, so that's another option. So we'll get to that when we finish the lecture itself. But I just want to use the opportunity to also show you that whatever the model that we fit is not good. Okay, even though the mixing seems fine, everything seems to be making sense overall. But if we dig a little bit deeper into how we actually fit the model in the first place and look at the posterior summary, it shows some issue with how we specify the prior in the first place. Okay? You can still do the hierarchical structure, that's totally fine, but it's more about, you know, the domain of, and the range, I should say, of the data, of the parameters that we're working with, and that has to do with how we give the priors in the first place. All right, so that's that. And another important topic that I want to mention for hierarchical modeling is what we call shrinkage or pooling effects. Okay, so I have a bunch of complicated code looking over here. You don't need to worry too much about what it is now. But the goal here is I want to visualize how the sample means, okay, which is the point estimates that we have of each of them, wouldn't be the MuJs themselves, but the average of the ratings in each of the schedule, and then compare that to the posterior mean that we actually analyzed that we showed you earlier. So I just want to use this chunk of code to show you the figure itself. So it is looking like this. Okay? So we're looking at the mean, okay? And on the right-hand side, we have the sample mean, okay, of the 4 different schedules, 1, 2, 3, 4. And on the left-hand side, we get the posterior mean after fitting the hierarchical model. Okay? So a quick discussion question is, what kind of, what do you see over here? Like if you're doing, for example, if you're doing a frequentist analysis, the right-hand side is all you get. So you get the sample means that, well, you can get some kind of hypothesis test or confidence interval, I guess. But the posterior mean that we're getting from our Markov chain Monte Carlo estimation of this hierarchical modeling show certain, I guess, patterns going on. So I'd like you to take a look and then discuss with your neighbors before we look at it together. I mean, the title of the section itself is called shrinkage pooling effects. So maybe that gives you some sense of what we're trying to do. And also remember, when we're using hierarchical modeling itself, we're trying to borrow information, okay? Like, for example, group 3, the schedule 3 is the Friday schedule that we only got 3 points, right? 3 data points. So we're saying that, well, with themselves, it might be really hard to do the analysis because of the small sample size, but we are using a hierarchical model. We assume that all of the mu j's come from the same normal prior. So we are essentially using information about the other schedules as well to understand the mu j. So that's the preamble. So take a moment. I will pause here and give you the chance to talk a little bit of what you observe on this graph. Maybe not a huge effect, I think, but some at least. So I would also give you an example of a bigger effect of the shrinkage later as well.
Not sure.
All right, any observations? Or maybe the effect is so minor that it doesn't seem to be hugely different. Like I said, at least the ranking, right, of the 4 different schedules about the mu that we saw in the posterior in the data in the sample itself do not change much when we're looking at the summary of that table. But overall, when we plot it like this, you probably can see a little bit what we call the shrinkage or pooling effects of when you have like a, say, schedule 4 that you start off with relatively high, right, sample mean, okay, because of the hierarchical structure that we're doing. The posterior mean of this schedule is getting pulling towards the center a little bit, right? And similarly, for the super small or super low schedule 3 that we start off, you can see that it's being put up a little bit to the center as well, okay? So this is the shrinkage or pulling effects that is built into the model when we're doing hierarchical model, because if you remember, we have the mu j, all of them follows the same normal. And then, of course, we estimate everything and all that. And from that summary table, we saw the differences a little bit. But this is an example that does not show too big effects. But if you check out a textbook, there they did a, I think, analysis of movie ratings, okay, by genres, okay. So over here, you can see that on the left, sorry about the reversed order, but on the left, this is the sample mean, okay, of, I think, 8 different movies. And then on the right-hand side is the posterior mean of all of that. And so here you can probably see a bigger effects of the pooling. Okay? And I just want to show you that this is kind of a expected outcome that you're going to see when you're dealing with hierarchical modeling. And we are essentially borrowing information across different groups to make more refined analysis or posterior analysis of the quantities of different groups. Okay. So that's one thing. Another way to think about the hierarchical model is think about the sources of the variability. So if I look at the Yij, if you remember, okay, we have this general model, right? We have the normal model with group-specific mu j, and then a shared sigma. So if you look at this model itself, just equation 26, that can be considered as what we call within group variability. Okay? What we mean by that is the sigma, as we know, is within each group is group J. All of our observations follow the normal with a particular mean and a sigma as the standard deviation. So sigma shows us the variability of observations within the group. That makes sense. Okay. Within group is within the group J in particular, but then you have all the different groups and all that. But nevertheless, the sigma is capturing the within group variability across the observations. Whereas if I look at the mu j, which we know follows a normal prior, this tau, as we know, is capturing what we call the between variability because we're capturing how mu j's are different from each other. Okay. So each mu j represents the mean of one group. Okay, we have 4 different groups going on, so we have 4 different mu j's, if you remember. So I want to show you, and some of you have taken advanced statistics course in the past, and you probably have heard about the analysis of variance, like ANOVA technique and all that. That is also talking about within group and between group variability. And I want to show you an analogy, I think, in this case, when you're doing hierarchical modeling, because equation 26 shows that sigma shows you the within group variability in the outcome. And tau, in the way that we set it up, shows us the between group variability. So when we set up or think about things in this way, a natural question arises is how can we understand the source of variability? Is the within group being dominant, or maybe the between group being dominant and all that? So if you have questions like that, given how we set up in equation 26 and 27, I hope it makes sense that, well, if we want to compare which one is more dominant, we can directly compare sigma and tau. Because sigma tells us, right, the within group variability, tau tells us the between group variability, and we have posterior jaws for all of them, for both of them, right? Once we have done our MCMC estimation, so we can actually directly compare them as a way to figure out which source of variability is more dominant than the other one. So if that makes sense to you, a particular quantity that you can do is this tau, is the battery, yeah. It's tau squared over tau squared plus sigma squared. So if we compute this R, think about it as a ratio, okay, of the within, I guess in this case, between group over the overall variability, then we can see which one is more dominant. So quickly we can do that. Closer the value of R21, the higher the between group variability, and then vice versa. Okay, so you can do this in R pretty easily. You can get the tau out from your posterior, you can get the sigma out, and you can calculate this R ratio. And then I did a quick quantile. This is the middle 90% posterior credible interval over here. So you can see that overall R is greater than 50%. Okay, as you can see the cutoff points and over here. And also we can do a graph pretty quickly as well, and overall you can see that the within group variability is dominant across the sum of these two. Okay, so that's just another way that you can analyze the source of variability. And I hope the biggest takeaway that I want you to remember is about how to set up and how to think about sigma and tau themselves. One as the within group variability quantity, and the other one is the between group variability quantity. Okay? And that has analogy in analysis of variance in other stats course that you've taken before. And hopefully with the way that we set it up, that sigma is showing you the within group variability, because that is the standard deviation of the data model, whereas tau is the standard deviation of the priors of the MJ, so that indicates the between group variability. Okay. Okay. All right. I think my iPad is dying. So with that, maybe I will, instead of use the lecture or use this to keep talking about, we can use the rest of time talking about lab 4, and then we can leave this exercise for next week. That should be no problem as well. So any questions about what we talked about so far? I mean, there's a lot of information, and lab 4, I think, will give you the chance to actually play with the code and play with 2 different priors. And then you will get a better practice, I'm sure, with running Jags. And I'm sure you're going to run into questions and issues and all that, but working through the lab will be hugely beneficial in that sense. Okay, so all right, so feel free to reach out when you have more questions later. Let me stop recording here.